Sounds deceptively simple, yet it sits right at the very heart of how our universe is put together. Why do electrons in the same atomic parking spot, what we call an orbital? Why do they always have to have their intrinsic wobble or spin pointing in opposite directions? Now, the material we've been looking at gets into some seriously mind-bending areas of quantum mechanics and particle physics, so don't worry, we're not about to drown you in equations.
No, definitely not.
Our mission here is to pull out the truly essential and, well, fascinating insights without making your brain feel like it's doing gymnastics.
Exactly. We're talking about the fundamental rules governing the tiniest ingredients of, well, everything. Think of this deep dive as your express route to grasping a key law of the cosmos.
Okay.
We'll be zooming in on two crucial ideas. This concept of electron spin and something called the Pauli Exclusion Principle.
Right.
These might sound a bit technical, but trust us, they're the keys to unlocking some genuinely surprising truths about the nature of reality.
Okay, let's start by picturing the world as we normally experience it. In our everyday lives, objects are distinct, right? If you have two identical coins, you could always, in theory, mark one and know which is which, track their individual journeys.
Sure, it makes sense.
There's no obvious reason why two identical things couldn't be in the same place at the same time and have all the same characteristics.
Precisely. But when we shrink down to the atomic level, the quantum world completely flips that familiar picture on its head. Here, particles like electrons have this bizarre wave-particle duality. They can behave like both waves spread out in space and like concentrated little particles. It's weird.
Yeah, that duality thing.
And their properties, like energy, are what we call quantized. Think of it like stairs rather than a ramp. An electron's energy can only exist at specific steps or values, not just anywhere in between.
Specific steps. Got it.
So that clear-cut classical view starts to get pretty blurry, in the quantum realm.
And that leads us to the intriguing puzzle of electron spin. Now, the name itself can be a bit misleading, can't it?
Very much so.
You might imagine a tiny electron literally spinning like a top. But that's not really the picture.
No, not at all. Electron spin is an inherent form of quantized angular momentum. It's a fundamental property of the electron, as essential as its electrical charge or its mass.
So that's not something it does.
Exactly, and something it fundamentally is.
Right. Here's where things start to get truly mind-bending, right?
Yeah.
How did scientists even think to conduct an experiment like Stern-Gerlach? That experiment was a crucial turning point.
Oh, absolutely pivotal. Imagine shooting a beam of silver atoms through a non-uniform magnetic field. Based on classical physics, you'd expect the beam to maybe spread out a little, like a continuous smear.
Okay, yeah, like tiny magnets getting deflected randomly.
But what they actually observed was that the beam split into two very distinct streams. Just two.
Two streams, not a spread. And what made that experiment so significant is that silver atoms have a single electron that's sort of on its own, right? So the atom's magnetic behavior is mostly down to that one electron.
Exactly, that valence electron.
The fact that the beam split cleanly into two spots showed that this intrinsic angular momentum, the spin, could only have two specific orientations when measured. We've come to call these spin up and spin down. So this groundbreaking result showed that electron spin isn't continuous, but comes in these two discrete flavors, which we describe using specific numbers called quantum numbers.
Exactly. To put some numbers on it, we have the spin quantum number represented by the letters S, which for an electron is always 12, a half-integer value.
Always 12. Okay.
Then the spin magnetic quantum number, Ms, can only take on two values, plus 12, which we call spin up, or minus 12, spin down. There are no other options. It's strictly in these two quantized states.
Just those two, plus a half or minus a half.
That's it.
And if we want to dig a little deeper into where this idea of spin comes from, it's fascinating that Pauli-Dirac's relativistic wave equation, I mean, that was a brilliant fusion of quantum mechanics and Einstein's theory of special relativity.
Yeah.
It actually predicted the existence of electron spin.
Yeah, it wasn't just tacked on later.
No. It wasn't just a convenient add-on to explain experimental results. It emerged naturally from a more fundamental description of the universe. That's pretty amazing.
It really is.
Yeah.
So we have this fundamental two-state property we call spin. Now, this leads to a really important division among the particles that make up our universe.
That's right. In the quantum realm, particles are broadly categorized into two families based on their spin: fermions and bosons.
The two big families.
Fermions are particles that have half-integer spin values, like 12, 32, and so on, Electrons, as we said, spin 12.
Yeah.
But also protons and neutrons. The building blocks of atomic nuclei, they're all fermions, too.
Right. All the matter particles, basically.
And bosons, on the other hand, have integer stain values like 0, 1, 2. Photons, the particles of light that carry the electromagnetic force, are bosons. Spin 1.
Okay. And this distinction isn't just a matter of classification. It's absolutely fundamental because these two types of particles follow dramatically different sets of rules.
Different rule books.
Totally different rule books. Electrons, being fermions with that half-integer spin, are governed by a statistical framework called Fermi-Dirac Exclusion Principle.
Okay, let's get to the core of our mystery then. The Pauli Exclusion Principle, often just called PP.
PP, yeah.
In simple terms, it states that no two identical fermions can occupy the exact same quantum state at the same time. Now, while this might sound straightforward, its implications for how the universe organizes itself are, well, absolutely enormous.
Huge. And what's truly remarkable is that this principle isn't some arbitrary decree of nature. It arises from a deep principle in the quantum theory of identical particles, the concept of indistinguishability.
Indistinguishability, meaning you can't tell one electron from another identical electron.
Exactly. Think about it. If two electrons are truly and utterly identical, then swapping them shouldn't have any observable effect on the physical state of the system. You can't tell you've swapped them.
Okay, that makes sense. You swap two identical things, nothing looks different.
Precisely. And this fundamental indistinguishability leads to the mathematical description of these systems using what we call wave functions.
Ah, the wave functions.
When you describe a system containing multiple identical particles, the total wave function, which essentially encodes all the information about the system, has to behave in a very specific way when you mathematically exchange any two of those identical particles.
A specific behavior upon swapping.
Okay. For bosons, the wave function is symmetric, meaning it stays exactly the same after the swap, no change.
Symmetric for bosons.
But for fermions, like our electrons, the wave function is antisymmetric. It changes its mathematical sign upon swapping.
It flips sign. -1 times the original.
Exactly. A factor of -1 pops out. Antisymmetric.
Okay, so what's the consequence of this sign change for fermions?
Well, let's imagine two identical fermions, like our electrons, trying to occupy the exact same quantum state, meaning they have identical values for all their defining quantum numbers. Same energy, same orbital shape, same orientation, and the same spin.
Trying to be in the exact same state.
Okay. If that were to happen, the math of the antisymmetric wave function dictates that the total wave function for the system would become 0.
0. The whole wave function just vanishes.
Vanishes. And a wave function of 0. That means the probability of that particular state existing is 0. It's a physically impossible scenario.
Ah, so the antisymmetry forces them to be different somehow.
Precisely. This mathematical necessity of having an antisymmetric wave function for fermions is the bedrock upon which the Pauli exclusion principle is built. It's not just a suggestion, it's a fundamental law arising from the very nature of identical fermions.
Wow. Okay, so the math itself forbids it.
The math forbids it. Okay, so we now know that electrons have this intrinsic spin, that they belong to the fermion family, and that no two identical fermions can have the exact same quantum state. Now let's bring this all together and see how it explains why electrons in the same atomic orbital must have opposite spins.
Right, connecting the dots. An atomic orbital, that region of space around the nucleus where an electron is most likely to be found, is defined by the first three quantum numbers. The principal quantum number n, which relates to the energy level. The azimuthal quantum number L, which describes the shape of the orbital, like SPI.
Right, spherical, downward.
And the magnetic quantum number, ML, which specifies its orientation in space. So these three numbers essentially give us the orbital's address, its energy, shape, and direction.
The spatial part of the address. Yeah.
So if two electrons are residing in the same orbital, they automatically share the same values for these first three quantum numbers, N, L, and ML. They're essentially sharing the same spatial and energetic room within the atom.
Same room, same energy level, same shape, same orientation.
Exactly. But we must remember the Pauli exclusion principle.
Oh.
These two identical fermion electrons cannot have an identical set of all four quantum numbers. They already have three in common.
N, L, ML are identical.
The only remaining quantum number that can differentiate them is M's, the spin quantum number.
The fourth quantum number, spin.
And since M's can only be +12, spin up, or -12, spin down, the only way for these two electrons within the same orbital to have a unique overall quantum state, and therefore obey the Pauli exclusion principle, is for their m's values to be different.
They have to be different.
One electron has to have a spin up, plus 12, and the other must have a spin down, negative 12. They need to have opposite orientations of their intrinsic angular momentum.
So the orbital provides the first three numbers, and to make the full set unique, the spin must be opposite.
Precisely. If both electrons in the same orbital were to have the same spin, say both spin up, they would have identical values for all four quantum numbers, nl, ml, and m's. That would be a direct violation of the PIP, making that configuration physically impossible.
The wave function would be 0. Can't happen.
Can't happen. Therefore, an atomic orbital can accommodate a maximum of 2 electrons, and those 2 electrons must have opposite spins to satisfy this fundamental principle.
Wow. It all comes together. So this seemingly simple rule that electrons in the same orbital must have opposite spins isn't just some arbitrary quirk of nature.
No.
It's a direct and profound consequence of some very deep and fundamental principles of quantum mechanics, the Fermion nature of electrons, and the Pauli Exclusion Principle arising from indistinguishability and antisymmetry.
And this isn't just some abstract concept locked away in the realm of atoms. It has incredibly far-reaching consequences that shape the entire world around us. It's not just atomic physics trivia.
Absolutely not. Let's consider the very foundation of chemistry, atomic structure, and the periodic table.
Yeah.
The Pauli Exclusion Principle is the gatekeeper that dictates how electrons fill those electron shells and subshells around an atom's nucleus.
The cosmic organizer.
Pretty much. If it were for this rule, all the electrons in an atom would simply cascade down to the lowest energy level, the 1s orbital.
Everything would just pile up in the basement.
Exactly. We wouldn't have the incredible diversity of elements and their unique chemical reactivities that we observe. Think about helium, element number 2. It has 2 electrons in its 1s orbital. They must have opposite spins to coexist there.
Okay, 1s is full with 2, spins paired.
Now, consider lithium, element 3, with its 3rd electron. Because the 1s orbital is already full with 2 electrons of opposite spin, thanks to the PPP.
No vacancy.
That 3rd electron is forced to occupy a higher energy level, the 2s orbital. This sequential filling of orbitals, always putting a maximum of 2 electrons with opposite spins in each, is what gives rise to the periodic trends in reactivity we see in the periodic table. Why alkali metals are reactive, why noble gases are stable. It all comes back to this.
That's incredible. The structure of the whole periodic table hinges on this. Yeah. And it's absolutely crucial for understanding how atoms link together to form molecules through chemical bonds, right?
Oh, definitely. When atoms form covalent bonds, they often share electrons in molecular orbitals. The stability of these bonds often relies on those shared electrons having opposite spins.
Spin pairing in bonds.
Yes, allowing them to happily occupy the same spatial region between the nuclei, which lowers the overall energy of the system. The pairing of electrons with opposite spins is often energetically favorable and leads to stable bonds. If they have the same spin, they'd repel each other more strongly or be forbidden from sharing that space effectively.
So stable molecules depend on it too.
If we connect this to an even broader perspective, in condensed matter physics, the study of solids and liquids, the PEP, is absolutely essential.
How so?
Well, it leads to the formation of energy bands in solids. Because electrons can't all pile into the lowest energy states, they fill up consecutive energy levels, forming bands. And the way these bands are filled or emptied dictates whether a material behaves as an insulator, a semiconductor, or a conductor of electricity.
Ah, so conductivity depends on the Pauli principle.
Fundamentally, yes. The very reason electrons can move freely and conduct electricity in metals is tied to the availability of empty energy states just above the filled ones for them to hop into, a consequence of the Pauli Exclusion Principle structuring those energy levels. And on a truly cosmic scale.
Cosmic scale?
Yeah. The degeneracy pressure that arises from the PP is what prevents stars like white dwarfs and neutron stars from collapsing under the immense force of their own gravity.
Wait, the same rule stops stars collapsing?
It's the resistance of fermions, electrons, and white dwarfs, neutrons in neutron stars to being squeezed into the same quantum state. They push back. This quantum mechanical pressure provides this crucial outward force against gravity.
That is genuinely mind-blowing, from orbitals to stars.
It even has implications in areas like magnetism, influencing how the intrinsic magnetic moments associated with electron spins align or anti-align in different materials, leading to phenomena like ferromagnetism, like in iron magnets.
Right, the spins lining up.
And in spectroscopy, the interaction between an electron spin and its orbital motion around the nucleus leads to subtle splitting of spectral lines, known as fine structure, which provides valuable information about atomic energy levels. It's truly astounding how this one fundamental rule, operating at the level of individual electrons, underpins so much of the complexity and behavior we see throughout the universe.
Yeah, what's so compelling is precisely how a principle governing the behavior of the tiniest particles has such far-reaching and tangible effects on the macroscopic world we inhabit. It truly highlights the deep interconnectedness of the universe across all scales.
Couldn't agree more.
Okay, so let's bring it all together. To recap our deep dive, electron spin is a fundamental quantized property of electrons, possessing two possible orientations we call spin up and spin down, plus 12 and a negative 12.
Check.
Electrons are fermions, a class of particles with half-integer spin that are governed by the Pauli Exclusion Principle, which dictates that no two identical fermions can occupy the same quantum state simultaneously.
The fundamental rule, yep.
Consequently, for two electrons to share the same atomic orbital, meaning they have first three quantum numbers, NL, ML, their spin quantum numbers must be different to ensure each electron has a unique set of all four quantum numbers, thus satisfying the Pauli Exclusion Principle.
One up, one down.
Hence, electrons in the same orbital must have opposite spins. It's a direct result of being identical fermions.
Perfect summary. And this raises a fascinating question for you to consider, for the listeners. How does this seemingly abstract rule governing the behavior of particles at the incredibly small scale ultimately give rise to the stability of the matter that makes up everything around us, the intricate complexity of chemical reactions, and even the possibility of life itself? What other seemingly simple and fundamental quantum rules might be operating behind the scenes, having equally profound and perhaps still undiscovered consequences for the universe we experience?
Yeah.
It really invites us to contemplate the profound interconnectedness of reality at its most fundamental level.
Absolutely. It's certainly something to keep turning over in your mind. Thanks for diving deep with us today.
My pleasure.
Until our next exploration, keep questioning.